This program is brought to you by Stanford University. Please visit us at stanford.edu.
This presentation is delivered by the Stanford Center for Professional Development, providing graduate-level education to working professionals, online, on campus, and on-site. For more information, please visit study.stanford.edu.
Today's talk is going to be about stream processing and how do you do computing in the multi-core era where there's several processors or cores on one die. And Professor Daly is a Stanford professor of computer science and electrical engineering and also the chair of the computer science department. He did his PhD at Stanford and was then a professor at MIT where he worked on the J machine and the M machine, which were new architectures. And then he came to Stanford and has continued research here with the Imagine project and Merrimac. Besides computer architecture, he also works in other areas, including high-speed signaling. And he has started a few different companies, including co-founding Velio, which works on high-speed signaling, which was formerly called chip-to-chip. And also, more recently, in the last couple of years, based on the Imagine research, he co-founded Stream Processors Incorporated. And so he'll be talking to you today about various topics in stream processing and what kinds of architectures are being developed. A few other things to know about Professor Daly. He is a fellow of the IEEE and a fellow of the ACM. He's received various awards from those organizations and others, including the IEEE Seymour Cray Award and the ACM Maurice Wilkes Award. He is chairman of Stream Processors and is also on the board of directors at Portal Player, which most of you have probably heard of. He's currently leading projects on high-speed signaling, computer architecture, network architecture, and programming systems. So he really has a lot of breadth in the computer science and electrical engineering fields, which is a nice talk for the seminar because the whole concept here is computer systems, and he has developed many computer systems. So please welcome Professor Daly.
Well, thanks, Eileen. One correction to the record, my PhD is actually from Caltech, although I was a student at Stanford many years ago. What I'd like to talk to you about today is sort of where we're going in the world of computing. This is a brief outline that I'm going to try to stick to during the talk. I'm not going to read it to you. Let me dive right in. Why is today different than 10 years ago or 20 years ago? People have been talking about parallelism forever. But there are a bunch of things that are fundamentally different now. So this gentleman is John von Neumann, and this is a picture taken in the 1940s with him standing next to a piece of a machine called ENIAC. In the late 1940s, John wrote the preliminary report on a stored program computer, and to first approximation, the machines that we've been building between then and now have followed his rough outline. A lot of the complexity that has gone into recent single-thread machines has been actually trying to do a little bit of magic work. It's sleight of hand, it's illusion to try to have parallelism going on under the scenes while preserving this illusion of things happening in sequential order. And this has served us well. We've gotten many years, from the late 1940s through the mid-2000s out of this single-thread paradigm. Why change now? This is a slide from an ISAT study I led in 2001 called The Last Classical Computer. I won't go into what the title is about. What it really shows you is why parallelism didn't catch on in 1980 when many of us were predicting that, we'll all have many processors on our desks by the end of the decade. But what it really shows is that through the 1980s and the 1990s, the blue line is that you were able to convert what Moore's law gives you. Moore's law doesn't say anything about processor performance, by the way. Moore's law says that you double the number of transistors on a chip every 18 months. And what Moore's law gives you is more transistors. And what we were able to do through the 80s and 90s is convert more transistors into better single-thread performance. The rate of 52% per year, if you dissect it, has three components. One component was by making pipelines deeper. If you started in 1980 with an 8086, these were all Intel processors that were used to draw this curve. In fan out of 4 inverter delays, a pipe stage, a clock cycle, was about 110 fan out of 4. By the P4, which is 2001, depending on whether you count the double pumped AOU or not, it was either 4 or 8. And that was actually overshoot of where you wanted to be. But it's clear that that's mined out. Once you've gotten down to 4 fan out of 4s per, per pipe stage, you're not going to cut it much finer than that. So that vein of instruction level parallelism was mined out. The other vein of instruction level parallelism that was in that blue line during the 80s and 90s was instruction level parallelism. The 8086 took about 10 clock cycles to do one instruction. By the mid-90s, people had machines that could do 4 instructions per cycle, although they rarely sustained more than one. There's sort of a 40x difference in instructions per clock over that period of time. The third component of that 52% a year remains with us, and that's faster devices. Devices are still getting faster, roughly 20% per year. But over this period from 1980 to 2000, because we also could make our pipelines deeper and make our pipelines wider with more instructions per clock, we were able to, without changing any of our software, turn Moore's Law's transistors into better processor performance and yield it on a single thread. The green line basically shows if you converted every additional transistor you got to performance linearly and took the 20% per year you're getting from faster devices as well, what you could get. This is kind of the ideal parallelism line. And even with parallel computers, you would never do this well. There's overhead that comes. You're not going to get linear speed-ups. But even if you could get perfect parallelism from tacking, as you get a bigger die, put more 8086s down on it, and you run them faster because the process gets faster, you would have only gained a factor of 30 over 20 years. But that has changed. What happened around 2001 is people realized that they'd mined out the pipeline depth. They had mined out the instructions per clock. And so all of a sudden, over the next decade, you're going to get to a realm where instead of being 30 to 1, it's going to be 1,000 to 1, and by 2020, it's going to be 30,000 to 1. So now there's a reason to go parallelism, and it's basically because we can no longer convert transistors to performance in a single thread. We now have to have multiple threads. The other reason for doing this is really one of power efficiency. So a lot of people are under the misconception that as you go to a finer line semiconductor technology, things burn more power. And they base this misconception on the fact that that's the way Intel processors work. Every generation, they tend to burn more power. This is a chart from Shekhar Borkar at Intel. In fact, Moore's original paper in Electronics in 1965 talks about power, and what he observes is that when you scale dimensions, say by 50%, what happens is you get 4 times as many things on a chip. If that was a processor, you now have 4 processors on a chip of the same size. It goes twice as fast, and it in fact burns exactly the same amount of power, because power and energy go as L cubed. So if you cut the line width in half, the energy of a switching event actually goes down by a factor of 8. Things get more efficient to first approximation as you scale line width. Now that's changing a lot as we run into leakage issues in some modern technology nodes. But to first approximation, things actually get better when you shrink line width. The reason why processors have been going up in power is because to squeak more single-thread performance out of a single processor, people have gone to heroic ends way beyond the point of diminishing returns, and that has driven the power up. Basically, if you take a simple processor and you shrink it from 130 to 90 to 65 nanometers, the power improves significantly at each stage, as does the performance. So people, both because they can no longer get performance out of single threads and because of the power issues, have kind of bitten the bullet. And all of the major computer manufacturers have said, okay, we're not giving up on single threads, but our major computer offerings going forward are multiple cores. And in fact, they've laid out roadmaps where now as you get more Moore's Law transistors, roughly every 18 months, you double the number of cores on the chip. So my projection is sort of 64 cores by 2010. And in fact, in a recent announcement by Intel, they say 80. So everybody agrees we're going to have lots of cores on a chip. And in fact, it's really the prevalent technology for everything from the embedded processors you're going to see in cell phones to the room-sized supercomputers that'll be at the national labs. They'll all be based on chips with many tens of cores by the end of the decade and many hundreds of cores by the middle of the next decade. So the interesting thing is that because many of us predicted that we would move to parallelism 20 years ago, a lot of work has actually been done on this. It's interesting. I was invited to a tab meeting at Microsoft this summer and a workshop at Intel last winter, both to look at, what are we going to do for multicores? And I came away from that with the thought that, gee, 10 years from now, these guys are, or not 10 years from now, 4 years from now, these guys are going to have 80 cores on a chip, and they haven't got a clue how to program them. And this was really kind of a frightening thought, and there's no excuse for that, partly because you can get 80 processor machines right now. This is actually a picture of a machine we built at MIT in 1991, the J machine. It's 1,024 processors, simple 32-bit RISC processors, with a fast interconnection network and actually a lot of interesting mechanisms for communication and synchronization. But the people who are designing these multi-core machines today are too busy designing them to go read the papers that people wrote in the 80s and 90s about how they should be built, and more importantly, about the mistakes that we made back then. And so they are obviously going to be sort of condemned to repeat those mistakes. What's interesting is that there is a lot of stuff that we do know from 20 years of research, or more actually. The research on parallel computing goes back to the 50s. We know how to build very good networks to connect the processing nodes together. We know how to build very efficient communication and synchronization mechanisms. There exist user-level communication and synchronization mechanisms that make it efficient to pass single-word messages from one task to another, and to do it every few instructions. You don't need to bulk your messages up to thousands of words to amortize overhead. That's an artifact of inefficient implementation. And we understand how to write simple parallel programs. But there's a fundamental problem, which is locality. And it's a problem that's becoming very large with the anticipated technology for multi-cores. And I'll go into a little bit more why that is. Part of it is that the problem has changed. This is another chip we did. This is our M-machine chip, which, if you want to talk about multiple cores, multiple threads, was 3 cores, 6 threads per core, again with efficient communication and synchronization mechanisms, done in '97. So one observation I'll make, having worked in parallel computing for a long time, is that parallel programming is not hard. It's very easy to write a parallel program. In fact, a while back, Steve Taylor and Manny Chandy at Caltech did an experiment where they taught their CS1 course in a parallel programming language. And the students had no problem at all learning how to write parallel programs, doing all the class assignments in parallel programming. What's hard is taking dusty sequential codes and converting them to parallel codes, because usually the logic of the program has things fundamentally wired into it in a sequential way. But programming in parallel is not hard. One thing that is hard, though, is to write an efficient parallel program, because efficiency requires locality. And locality is the thing that's fundamentally hard in getting in multi-cores to work well for you. But it's not all a software problem. I think if you want to exploit locality and you want to write good parallel programs, the right hardware makes doing the right software a lot easier. So let me move to the next phase of the talk. We've now established that we are moving into the multi-core area due to these trends of mining out sort of covert parallelism. We now have to be overt about our parallelism, and due to the power and efficiencies of building hugely out of order machines. Now let's look at sort of what type of architectures the technology today is driving us to. So what is the canvas that we get to paint on as computer architects? So here it is, probably slightly obsolete, 90 nanometers. I should update this slide to 65. But if you have a 90 nanometer chip, say 12 millimeters on a side, which is kind of a friendly size for manufacturing. By the way, the Hero microprocessors are like 18. And you can actually manufacture this for well under $200 in quantity. This is how big a 64-bit floating point unit is. This is to scale. Arithmetic is really inexpensive. So if you look at the amount of die area that is, and amortize at $200 over the die, a gigaflops is 50 cents. You ought to be able to buy 50 cents per gigaflops. And by the way, it also dissipates about 50 milliwatts going at a gigahertz. So a gigaflops is also 50 milliwatts. So why is it that when you go out and you buy a machine for scientific computing, something that would sustain a gigaflops, it's not clear you can actually do that on any commodity processor today, costs you many thousands of dollars, not 50 cents, and burns many hundreds of watts, not 50 milliwatts. And the reason is this arithmetic doesn't matter. That's not what's costing the money. It's not what's burning the power. What matters is moving data around. But also notice that if you want to get performance out of this chip, you don't do it the way things used to be, is you build a more powerful processor by building a multiplier that could operate in fewer cycles, or putting more of your floating point unit combinationally rather than sequentially on the chip. Today, this is a fully pipelined floating point unit, can start a multiply and an add every cycle. You've already done all of that, and you can still put 400 of them on a chip. So it's clear that if you want a higher performance machine, that performance comes from parallelism. The reason why you don't get 50 cents and 50 milliwatts per gigaflops is that the communication dominates the arithmetic entirely. Many machines are built by this old ratio that for every gigaflops of performance, actually the old ratio was for every megaflops of performance, you wanted a megabyte of memory and a megabyte per second of bandwidth. And these ratios are warped because they were coined by Gene Amdahl in the 1960s when the arithmetic was the thing that cost a lot. If you're balancing a machine by those things today, you'll wind up with one floating point unit surrounded by enormous numbers of caches and enormous numbers of memory channels to try to get all of this bandwidth into that floating point unit. And if you do sort of a balance instead by diminishing return on investment, which is the way any sensible business person would invest in their chip, instead the question you'd be asking is, if I invest the next square millimeter in a floating point unit, what will that return me in performance versus investing the next square millimeter in another couple tens of kilobytes of cache? What will that buy me? And you'll wind up with a lot more than one floating point unit, and it won't be balanced according to the 1960s rules of thumbs of balancing machine, but it'll be a lot more balanced from a cost performance point of view. Because if you try to get the bandwidth to feed these floating point units off chip, it's prohibitively expensive. It's $8 per gigaword per second, if you look at it that way, 16 times as expensive to do that. So you don't want to transfer all those words off chip. You need sort of at least a 20-to-1 ratio of words per second of off-chip bandwidth to operations you're performing on chip. And by the way, since each of those operations requires 3 operands, 4 for a multiply add, you actually need to multiply that number up again by a factor of 3 or 4.
What about heat for communication versus computation?
The heat for communication dominates as well, and I'll show some data on that shortly. Power increases with distance, and I'll actually show some quantitative numbers with that. Latency is also a big factor here. This is also to scale how far you can go in one clock on this chip. So it takes you sort of look at that, 4 or 5 clocks to get across the chip on one edge and 4 or 5 clocks on the other edge. So if you want to do things, you have to be doing it to data that's near you. You can't be traversing the chip every time you need to get some data. Now it turns out that the way to hide this latency is with parallelism. As long as you can do a lot of things in parallel, you can tolerate a lot of latency. But what you can't hide is a lack of bandwidth. You only have so much bandwidth off chip, and also globally on chip. You have much more bandwidth to things close to you than you do going a longer distance, because it takes more wire to get there. You're burning up more communication resources. So this should answer your question about, the question was, how does power vary between doing things on chip and doing things off chip? And these are all for 64-bit transfers. So I consider a word to be 64 bits. At a gigaword, basically gigahertz 64-bit transfers through various levels of memory hierarchy. This was a set of numbers produced for 130 nanometer technology, and it scales roughly linearly with technology, not exactly, but close enough. And what you'll see is that reading a register is cheap compared to a floating point operation. It takes about 10 picojoules rather than 50 picojoules for the floating point operation. But if I have to cross 2 millimeters of wire to go to something just in a different region on the chip, that's as expensive as doing the floating point operation, communication-wise. If I've got to go globally on the chip, say 15 millimeter wire transfer, that's 4 times as expensive as a floating point operation. And going off chip is 20 times as expensive. Going globally, which means not just off chip, but across some interconnection network elsewhere in the machine, I'm up to a factor of 100 more expensive than the arithmetic operation. So again, communication dominates both in cost and in power. The goal then is to minimize communication. So if you remember nothing else about this lecture, you should remember this slide, which is, given the constraints of modern technology, the way we get performance is through parallelism, right? We're not going to squeak anything more out of doing things out of order to issue things, and actually that was parallelism anyway. The way we get performance is by putting tens to hundreds of arithmetic units down on a chip. But the way we get efficiency is through locality, because the only way we can keep those arithmetic units fed is by feeding them with data that is right next to them, only rarely going globally on the chip, and even less often going off chip to get that data. So next segment, we've talked about why we're moving into the multi-core era, what the constraints, the technology drives us that forces us to think about parallelism and locality. Now let's talk about what type of architecture that drives us to. So if we can build these inexpensive 50-cent gigaflops floating point units Obviously, we want a lot of them. Those are the little blue dots. And since we need to feed them locally, we need to put registers right next to them. That's actually included in the blue dots as well. Think of every blue dot as a floating point unit and a small number of registers sitting at every input of that floating point unit. And then what you need is a hierarchy, because when you can't keep the working set in those sets of registers, you need another set of registers close to it. So when you sort of need to stage data in here, you need to go to that register set. Why does it need to be close to it? Because the capacity of the registers in the blue dots has to be large enough to cover the latency to the green rectangles, right? The size of a register file is driven by two things. It's driven by the need to supply what's downstream from it, and the need to tolerate the latency to what's upstream of it, to the next higher level in the hierarchy, right? If you try to go all the way off chip with this, that latency is too high. These register files would get really big and the whole thing breaks. So you have to introduce the intermediate level here, and then I've drawn another intermediate level, the red one here, where you basically stage into the green one from the red one, and the green one is big enough to tolerate the latency it takes to access things from the red staging of memory. And by the way, its size is driven by that latency and driven by working set considerations. Then the big purple one, and this chip would have several of these, but I got tired of drawing little squares at some point in time. Question?
Can you just give us some idea of what plausible numbers are for some reasonable stage of the technology?
Right. So later on in this talk, I'm going to give two case studies, the Stanford Imagine and Merrimac projects, and I'll give specific numbers for the levels of hierarchy there. So if you hold on to that part of the talk, I'll give you specifics. Anyway, this is sort of physically what it looks like, and I want you to keep the physical view in mind because it's very important. But being computer scientists, who were once monkeys who hung upside down in trees, we abstract this and draw it from a tree. And if you're a monkey hanging upside down, trees have their roots at the top instead of at the bottom. And so the view of the machine from an abstract point of view is a tree. Or at the bottom level of the tree, we have these floating point units. Right next to every floating point unit, again, part of the blue dot, we have register files dedicated to that floating point unit. And then we have various levels of switching and the next level of memory, a regional memory, a chip memory, local memory off chip, and then finally global memory anywhere in the machine. So this is basically, by having your architecture express the memory hierarchy this way, it's empowering. Right now, you don't have this. For most machines today, there's a lot of memory. It's physically distributed on your chip, but you can't see that. All you see is a linear memory hierarchy. There's an L1, an L2, maybe an L3, and then DRAM. But it's actually important if you're in the L1, whether you're on this end of the chip or that end of the chip. You have no control over that and can't even see it the way most of these architectures are. This, if you view this as sort of the L1 or maybe the RM as the L1, which one you're in matters because it's close to some arithmetic resources and far from others. And if you want to choreograph your movement of data, you want to make sure the data is put near where it's going to be used. Okay? So by having an architecture like this, we now give you control over the movement of data, and that lets you optimize it. To move on, a lot of people would say, I like this organization. Just call each of these a cache. Register file L1, L2, L3. Everything works fine. But it doesn't. And the reason it doesn't work fine is that our critical resource here is bandwidth. And caches squander bandwidth. And they do it in a number of different ways. They also don't hide latency well because with a cache, you wait until you need something, and then you ask for it. If it's in the cache, great, I get it in one cycle. But if it's not in the cache, things are really, really bad. If it's not in the L1, it's 20 cycles to the L2. If it's not in the L2 or the L3, and a lot of modern processors, it's close to 1,000 cycles to DRAM. And that gets to be an extremely painful process that you can't hide. The most aggressive out-of-order machines do not hide 1,000 cycle latencies to DRAM, nor can they stack up enough references. So they actually waste both arithmetic opportunities and memory bandwidth because the memory pin's idle while you're on one of these long misses. You haven't generated enough pieces of work to go out and request more bandwidth from the memory. So they waste bandwidth. The next thing that they do is they don't use your on-chip real estate very efficiently because at any given point in time, if you look at what's in a cache, some large fraction of the dirty lines are dead. Dead in the sense that the data by a compiler analysis has been used and will never be used again. But it's marked dirty, and so if you want to replace what's in that line, unless you have some very clever cache, you are going to generate the memory traffic and write that dead but dirty data back out to memory. And then finally, what's in there is not optimally staged to sort of bring it in just in time. You either bring it in too early or too late. So by all three metrics, you're not using things well. And so let me give you an example based on one of the codes from our Merrimac project, a finite element code written by Tim Barth at NASA. And I've done a very simple cartoonish sketch of that code here. I'll show actually a graph of the full code later on to give you an idea of why this is, why caches are not a good way of managing memory and why doing it explicitly can do much better. So this code, very loosely sort of loops over all the cells and computes flux. And then it loops over all the cells and computes a function of the flux. What's interesting is when you look at a lot of these codes, if they originally came out of a Fortran code, this one wasn't. This one was written explicitly for Merrimac. But they all made many passes over the whole data structure. And the reason they did this is that Fortran programmers understand that you can put loops in functions, but you can't put functions in loops. Sorry, that's far too inefficient. So instead of just incurring a little bit of function call overhead, they incurred the overhead of visiting every cell of the data structure for every function they apply to the cell. And so the first thing you do when you analyze these codes is you turn that inside out and make it so you visit every cell once, since that's the important thing, and then milk that cell for everything that you can by applying every function to it within that loop. In any case, the way we typically view this, this simple view here is that we have two functions, function one that's computing a flux and function two that's using a flux. We will block the code, and our compiler knows how big these intermediate levels of memory are. I've called it a stream register file here. This is the term we use for those intermediate levels of memory in stream processors. And so we'll gather the first block of cells. We've chosen the size so that it and all of its sort of products will fit in this intermediate level of memory. We'll issue the gather. Sometime later the gather will finish and we'll have the cells in this intermediate level of memory. And then we'll fire off the first function. We call that a kernel. And that kernel runs, and before it runs, everything it needs is on chip. All of the data it needs is in the stream register file. All of the instructions it needs have been explicitly loaded into the memory. And so there's no surprises. In fact, if you look at all the complexity in modern processor design, it's all due to sort of dealing with surprises. Data surprises that happen when you miss in the cache, and control surprises that happen when you mispredict branches. And really, a lot of what stream processors do is that they relegate all surprises out into this realm of the world. And then once things happen on here, they're extremely predictable. And this gives your compiler a great deal of power because it can then orchestrate things down to the clock cycle. So we fire off kernel 1. It produces the flux. It produces it into the stream register file. Once it's done producing the flux for this block of cells, we fire off kernel 2. It updates the cells. And notice that kernel 2 also has everything it needs on chip. The flux is there, and the cells are there, so it doesn't have to go out to memory at all. And then finally, we'll scatter the cells back to memory. Now, there are two ways that this wins over a cache. I'll go into this in more detail. Probably the most important is the flux never touched memory. It isn't because there's any reuse. In fact, in most of these cases, each word of the flux array is written exactly once, and it's read exactly once. And in fact, that's almost a worst possible case for a cache, because the way caches work is the first time you write it, unless you have sort of non-allocate, you'll actually go out to memory, you'll read the line in, so you can then write the word of the line. It's now dirty. Okay? You read it once, it's now dead, but it's dirty in your memory, so at some point in time you'll write it back. So there were two cache lines of memory transfer for every cache line touched during this flux operation if you did it with a cache. Here you never cycle the memory because the compiler knows it can allocate this array in the stream register file, materialize it there, consume it there. It's now dead. You don't have to worry about it anymore. So that's the first thing. The other thing is, even in the cases where you had to go out and get a piece of a data structure from main memory, in the case of gathering the cells in and scattering the cells back, you were able to do this explicitly and have everything there when you needed it, so there were never any misses. I think that these balloons now say all of this. Okay. So let's look at sort of how this happens in a schedule. So this unrolling in time. What we do is we software pipeline these loops. We actually software pipeline them at several levels. Within kernels, they're software pipelined, but also we software pipeline the invocation of kernels and memory operations. So we overlap the memory operations shown on the left with the kernel operations showing on the right. So after we've loaded the first set of cells in, doing those gathers, we can gather the second set of cells, labeled cells sub 1 here, while we do the update computation on the first set. While I do the flux computation on the first set, and then store them back while we're doing the flux computation on the second set. So everything we need is on chip here. No misses, no surprises, all very deterministic. And I'll actually show later how we can use that to advantage in the compiler to come up with very efficient schedules for what goes on. On the right side is what happens when you do this with a cache, which is, so I've got a great cache hit ratio, 99% hit rate. Well, that means 1 in 100 will miss, right? And I'm doing lots of things in parallel, so I miss pretty quick, because I'm doing hundreds of things in a cycle. It means a couple cycles in, I've got to miss. When I miss, that takes at least hundreds of cycles, in some cases these days close to thousands of cycles. And each of those thousands of cycles, there were hundreds of instruction opportunities that I now can't do. So when I miss, that penalty now is tens of thousands to hundreds of thousands of operations that could have been executed and aren't. So even though 99% sounds like a great hit rate, it's nowhere near adequate to keep your machine busy on an application like this. The analogy I like to use here is very often I'm tasked on weekends to fix things around the house. And a while back we had sort of a plumbing emergency. And so you sort of, if you think about it, you look at the job and you say, okay, I'm going to need some 3/4 inch pipe and 3 copper elbows and this union and make sure I have flux and solder and propane. You make the whole list. You go to the hardware store once, you get everything, and you come back. That's really what the stream processor is doing. It's deciding everything it needs to do the computation. The compiler is figuring it out in advance, bringing it in, and then it executes without interruption. On the cache approach, on the other hand, you say, oh, I'm going to need some pipe. You drive down to the hardware store and come back with your 3/4 inch pipe. You get the tubing cutter out and you cut a couple pieces, and then you say, oh, I need an elbow to go on this. Get back in the car, drive to the hardware store, come back with the elbow, and you get the picture. 10 trips to the hardware store later, you may actually be finished with the job. But that's really what a cache does. It sort of reactively gets the next thing it needs without looking ahead, predicting and getting the whole bulk. So that was an interesting analogy. How in fact do we program these machines? So let me talk to you a little bit about sort of the history of how we've done it here at Stanford. That again, we're trying to achieve parallelism and locality, and also along with those predictability. So one way we view things is as a stream program where we have kernels that do operations on data, and they pass between them streams of data. Much like in the finite element code, a stream of data was the set of cells you're operating on or the set of fluxes produced by those cells. And this gives us a couple types of parallelism. First of all, these streams expose data parallelism. The data set is usually large. It's typically many millions of cells. And so you have all the data parallelism you could possibly want to keep all of your many hundreds of ALUs per chip busy. The next level of parallelism is what we call task parallelism. So if operating at 1 million things in parallel wasn't enough for you, I can be operating on some of them in kernel 1 and others in kernel 2 and 3 at the same time. So I can have control parallelism as well. And then finally, within each of these kernels, you can analyze the code, and there is some instruction level parallelism in there, often as much as a factor of 5 or 10. So the multiplication of all those gives us all the parallelism we could possibly want to keep our many ALUs busy. Parallelism is usually, not always, but usually not the problem. The bigger problem is locality. And again, this exposes 2 types of locality for us. First of all, within one of these kernels, everything is local to the kernel. One of the restrictions we have in writing kernels in all the 3 programming systems I'm going to show you is that a kernel can't make a random reference to memory. The kernel can only reference things in stream-C, kernel C, or Brook that are in its input streams or output streams. And in Sequoia, in the blocks of memory it has localized. That really saves a lot because now everything that's going on in this kernel is local to this kernel. I've captured the locality in the bottom level of the memory hierarchy. The other locality that's exposed here is producer-consumer locality. Because if I have a stream of results produced by one kernel consumed by another kernel, I know the lifetime of that stream, right? It's from when this kernel writes it to when that kernel reads it. If this stream doesn't escape those 2 kernels, as soon as I've read it with that kernel, I can deallocate that storage and I don't need it anymore. And therefore, if I can block those streams to the right granularity, I can capture them entirely in some relatively low level of the memory hierarchy. So here's sort of a brief history of stream programming at Stanford. In 97, we developed a programming system for Imagine based on a pair of programming languages called Stream C and Kernel C. And the notion here is that you broke programs into kernels and streams, much like the diagram on the previous page. The Stream C was actually a superset of C++. You could write anything you wanted, plus declare streams and kernels. And then kernel C was the language you wrote to write the kernels, which was a subset. You were restricted in not being able to make these random memory references outside of the kernel. You were restricted in what you could access within that kernel. Using Stream C and kernel C, we developed a couple of the key compilation technologies for stream programming, one called communication scheduling, which basically choreographed the movement of data in a distributed machine where you have several independent memories and you want to move data between them, and one called stream scheduling, which really dealt with how to stage memory up and down this memory hierarchy. In 2001, when we started the Merrimac project, we realized that Stream C kernel C was far too tied to the hardware. There was a lot of pieces of Imagine that showed through into the programming language that lacked portability. And Brook was designed as a language which would be much more elegant, easy to use, machine independent. It was fairly successful in that respect. It actually spun out and has a life of its own as a subset of Brook called Brook GPU, which is on SourceForge and has been downloaded tens of thousands of times and used to program general purpose applications on NVIDIA and ATI graphics cards. But one thing we found with Brook is that it was too one-dimensional, as were Stream C and kernel C for some of the scientific applications we wanted to address with Merrimac. And around the same time, largely due to the work of Keyvan Fatalian and Tim Knight, we saw that there was nothing fundamental about being one-dimensional, about having streams be a sequence. What was fundamental was that you localized all the data you needed for a kernel and then executed the kernel. So in Sequoia, we generalized the notion of kernels to what we call tasks. And the difference is, instead of being associated with a stream, which has this notion of a linear sequence to it, a task is simply associated with a number of blocks of data. And in Sequoia, you write a set of tasks that recursively decompose these blocks of data until you have a set of blocks of data that will fit in the bottom level of the memory hierarchy. And then you invoke what we call a leaf task on it, which actually does the work. I'll give you an example of this in a few minutes. And this really generalizes things in a nice way. It's hard to do things like an outer product in Brook, Stream C, kernel C. It's quite easy to do that in Sequoia.
How long did it take to compile applications?
That depends on the programming system, and it basically is comparable to other compilation systems down until you got to the kernels. And some of the kernel compilation technologies took a while to compile because they did very exhaustive searches. So let me talk a little bit about a couple of the technologies, software technologies here, and what they enable. This is a really nice example of what you can enable by a combination of architecture and software. So one of the big things about a stream processor is that you factor the surprises out of the inside of the machine. In fact, all the memory surprises happen out at this level of bulk operations. Whether you're going to have a bank miss in the DRAM, or whether you're going to have a cache miss, or any of those things, you don't see when you fire off a kernel. Everything is localized in compiler-controlled memory. Some replacement algorithm didn't accidentally throw your data away because the stack walked over it. And because it's locked down there, the compiler can exactly predict how long it's going to take to get to things. And it can do an extremely good job of static scheduling. So this is taken from the stream fem code again, the compute cell interior kernel, which is where the bulk of the time is spent in this code. And what you see, this is sort of how one iteration looks. It's in software pipeline, where this one iteration of about 120 cycles is folded down on itself. You actually see that there's 320 cycle initiation intervals here. And so the whole one iteration of the loop takes 360 cycles. We fold 3 iterations on top of one another with software pipelining and get the resulting schedule over here. And what you see, these are the 4 multiply-add units, floating point multiply-add units on Merrimac, is that they're busy nearly every cycle. The occupancy here is over 95%. In contrast, running the same code on a state-of-the-art x86 machine, it sustains something less than 5% of performance. And that's because it winds up, even though this code is such that if you stage the memory right, you can get by with the memory bandwidth those machines have, the reactive nature of trying to feed the ALUs and the centralized nature of the structure that's feeding them will not sustain this kind of performance. So the ability to statically compile the code occurs because we've factored things out. The technology that's going on under here is something called communication scheduling. Takes into account the fact that these 4 multiply-add units are actually fed by 12 separate register files, one on every input of every function unit, and the communications have to be scheduled from the outputs of function units over switches into the appropriate register files for where the next operation takes place. It's actually an interesting compiler technology. The other neat compiler technology really is having to do with how to manage the on-chip memory. This is sort of the full StreamFem application shown up here in sort of diagram form. And on this side, I'm showing the on-chip memory, what we call the stream register file. And time goes vertically here, and space goes horizontally. And what I show is that at any given point in time, the compiler has sized the blocks so that nearly all of the on-chip memory is full of live data. If any data is dead, we reallocate its space to something else. And it's staged things much as if it was trying to do just-in-time inventory management. The only thing worse that you can do than loading data too late is to load data too early. Right? If you load data too early, it's occupying your valuable on-chip memory when it didn't have to. You could have used a larger block size or gotten some other data set in there. So it's not good to load it late, but it's also not good to load it too early. You want to load your data just in time so that you don't tie up any more sort of bytes time cycles than you need to in your on-chip memory. And so the stream scheduling technology is able to do this by sort of looking ahead and looking back in the schedule and decide exactly when it needs to initiate a load, how much of memory it needs to do that, and then it does an iterative search to find the right block size to do those loads. Yeah, question?
Would you recommend relying on this static schedule for correctness or only for efficiency?
So it's guaranteed to be correct, but the reason why we're doing it is for efficiency. Because it's much more efficient to have a compiler solve the combinatorial optimization problem well of how to pack your on-chip memory in time and space.
If the compiler made a mistake with the hardware, throw in the wait cycles for the data to arrive, or would you just
there are interlocks on all of these things. So yes, we do actually interlock them. But the main point here is an efficiency point. That if you rely on doing this in a reactive method, you get a very suboptimal allocation of time of storage time and space. That's a good question. Yeah.
There seems like there's an unstated assumption about what kind of application we're trying to speed up. It has to be an application that can be expressed in such a way that the compiler can usefully statically schedule it. Are we assuming large matrix codes with very regular structure? I mean,
no. So there is only one thing you need to have an application be coded in this style, and that's that there has to be a lot of parallelism. I particularly chose StreamFem because StreamFem is an irregular code. Everything here is gathers and scatters. There are not regular matrices. You're taking arrays of pointers, index arrays, if you want to think of it that way, and randomly referencing memory, gathering the data in, operating on it, and then scattering things back out. So you don't need regular matrices. You don't need linear or predictable strides. All you need is parallelism. In fact, pointer chasing codes work just fine as long as there are enough pointers to chase in parallel. Conditionals work just fine. This isn't about codes with little control flow or about codes with regular data access. It's all about codes with enough parallelism to keep the units busy. So let me go on and talk a little bit about Sequoia. Since I hear everybody's watch is beeping 5 o'clock now. Okay, I got plenty of time then. Maybe I'll slow down. But it's always good to have time for questions at the end. So this is sort of a bottom-up way to view how a Sequoia program looks. And I'm showing it sort of in relation to an IBM cell, which is what we're using currently as our target for the Sequoia programming system. So the cell has 8 synergistic processing units. I like to think of them as stream processing units. Because otherwise it sounds like a Toyota hybrid vehicle or something. Each of them has a local store, which I always forget whether it's 128K or 256K bytes, but it's 256. Okay, it's less than you would like because your code has to fit in there as well. And so in Sequoia, what we do is you write a leaf task, and the leaf task is just like any other bottom-level thing. In this case, we're doing matrix multiply. And so it's just the triply nested loop that's computing the elements of C as a product of the correct elements of A and B. And this is going to run in each of these SPEs, and it's only going to touch things in that local memory, right? Everything is local. Both all the code and all the data it needs are there before it fires off, and everything is wonderful. Now, to get to that point, you wrote an inner task. And the inner task's sole job is to recursively subdivide the program to the point where everything fits in that bottom level memory, and then you can invoke the leaf task. And so this is the Sequoia code for the inner task, which is sort of conceptually running in either the aggregate local store or the node memory. Right? You'll actually run this recursively. You'll start it in the node memory. It'll subdivide things so that they're big enough that they fit in the aggregate local store, which is basically sharing the local stores across the 8 SPEs. Then you'll run into the aggregate local stores, and it'll block it again to fit into an individual local store. And what it does is it uses these variables called tunables. Here we have 3 tunables, u, x, and v. And what it does is it chops a up by u and x. It chops b up into xv size quantities, and it chops c up into uv size quantities. And then it does a map par, which means do all of these things in parallel, from I up to m over u. And map reduce, which says do all of these in parallel and then sum the results of applying matrix multiply. So this is actually a call to itself, right? Because this is the matmul thing. And so when you're at the outer level, when you do this matmul call, it calls the inner task again and does a recursive subdivision. When you're at the aggregate local store level, it calls this version of matmul, the matmul leaf, because now you're small enough that you can do the leaf. Now what's interesting about this is it's machine independent. All of the knowledge about how big a local store is in cell, or even how many levels of the hierarchy they are hidden in these tunables. And so right now, the way our programming system works is we set these manually for each level that we instantiate inner tasks in a mapping file. So you have the source file, and then you have the mapping file that goes along with it. And actually, one of our research topics is how to set these tunables automatically, or at least to give the programmer tools that they can use to ease the task of setting them. But this exact same code can run on cell, and does run on cell, and can run and does run on a cluster of P4s using different tunables to deal with the different memory hierarchies that it's mapping to. So let me talk a little bit about our experience here at Stanford across 2 projects in playing with stream processors. And so I'll start with the Imagine. Hello. Okay. So Imagine was our sort of first foray into stream processors. And I should say the way the project started is I was very interested in computer graphics when I took a sabbatical to the University of North Carolina in 1995. And was playing around with a lot of different graphics algorithms. I was playing around with some image-based rendering algorithms and some surface subdivision algorithms. I was extremely disappointed that graphics hardware of the day would just scream as long as what you were doing was rendering textured polygons. But as soon as you wanted to render surfaces from sort of point clouds, or if you wanted to do a subdivision surface, they just ground to a halt. You would get no value out of them at all. And so I asked the question, what we'd like to do is build something that's programmable, so we can program all these different graphics algorithms, but gives us the same performance, measured in some abstract way, as if we'd hardwired it to render polygons. So we asked, well, why are the hardwired polygon renderers so fast? Well, it's simple. They've got a lot of ALUs, and they feed them, one ALU feeding directly to the next through some, either directly or through some small scratchpad memory that's right next to it. And again, it's the 2 basic principles, parallelism and locality. And they're much easier to exploit when you only have to run one algorithm. But it's not hard to generalize them. So what we chose to do was to develop a machine that could expose parallelism and locality, but do it in a programmable way. Imagine, I don't have block diagrams up here, but you can see almost from the chip floor plan up there that there are 8 arithmetic clusters. Those are 8 things vertically. In every arithmetic cluster, there are 6 32-bit floating point units. So there are 48 floating point units in Imagine. In each cluster, there's 3 floating point adders, 2 floating point multipliers, and 1 floating point divide square root unit. And in each of those, associated with each input of each floating point unit is a small 32-bit by some number. I think they vary. I think most of them are 16 deep register file. And there's a switch then that connects those together. And so it's exactly that tree structure. The next level of the tree is a stream register file, which is a large structure just to the left of the array of clusters. And then there's a memory system with 4 synchronous DRAM channels going off to memory off the left side of the chip. So we co-developed Imagine with the Stream C kernel C programming system. And so it was again, one of these things where, because you're building the hardware, you can enable good software. So we were able to enable being able to do these stage transfers, being able to execute from stream register file to stream register file without allocating in memory. We built as a 21 million transistor chip. It's really in a 0.18 micron process with 0.15 micron devices. And we got the chips back on April 1, 2002, no fooling. And they worked. And one thing that we did is we benchmarked them against an NVIDIA chip of the same era with the same transistor count, also in a 0.18 micron process. And it was a dead heat. I think they beat us on fill-limited things, and we beat them on vertex-limited things. But we were very close to the performance of hardwired graphics processors. But by the way, there was also a ray tracer built to run on this, and a subdivision surface rendering algorithm, and a bunch of other things, as well as a UMTS modem, several video codecs, and some image understanding algorithms. So you had the flexibility of being able to program arbitrary things, and yet you were matching the efficiency of things that were hardwired. Here's some data that sort of shows how we were successful and where there was room for improvement. This shows for these 5 algorithms a stereo depth extractor, an MPEG codec, QRD, which was really the bulk of the time spent in a DARPA phased array antenna application called STAP. Pat Hanrahan's real-time shading language, which was adapted to run on Imagine, sort of a predecessor of NVIDIA's CG, and then the average over all of these. Now, the good news to take away from this chart is that most of the time is spent in the kernels, because the white plus the yellow plus the orange is all in the kernels. So it means that we were very effective at not spending time blocked on main memory accesses, right? That would be memory stalls, the light gray region, which is actually pretty small, or on dependencies between control. That's the darker gray regions. So we had reduced the problem of getting good efficiency in these applications to getting good kernel efficiency. Now the bad news is that the overall efficiency wound up being roughly 50%, which is not bad. I mean, very few machines sustain 50% of peak across a range of applications, but we were not happy with that. We had set much higher goals for ourselves. And the reason it is because we're spending too much time in loop overhead. And so the way to look at it is that the yellow area is kernel main loop overhead, and the orange area is kernel non-main loop overhead. Ignore the orange. It's actually a pretty small effect. The yellow area is really big. It's where most of our overhead is coming from. And it's coming from that because when we block our algorithm, we block our data structures to fit in the stream register file, the blocking is too small. So we're spending too much time on loop preambles and not enough time in the loops. And that's really what's going on with the yellow and the white. And that could be fixed by just cranking up the size of the stream register file, at some penalty in die area. But if you look back at the die size, at least for this chip, hello, page up. Okay, overshoot. Be patient. Control input, wait for it to respond. It's like, okay. It's going to get there one of these days. If you looked at the die photo, you'll notice that the SRF arrays. I wish I had a pointer here. I don't know if I can use the mouse. Do you have a mouse here? Yeah. A pointer would be great. But the SRF arrays, which are right in here, that's a memory array. If you doubled the size of that, it would cut the size of those yellow bars in half, and it wouldn't have made a tremendous impact to the area of the chip. Okay. So that was really, I think, a success story in being able to take a wide range of algorithms, some of which with truly hairy control structure. Oh, thanks. Oh, it looks a lot like a battery. I hope I didn't just drop the end off of it. Okay. Okay, so how do I turn it on? Oh, button. Okay. I'll try not to blind people, and if I do blind you with your remaining good eye, look at the slide. Okay. So here we're able to get good performance across a range of applications. And one of the reasons we're able to do that is because the software was really able to take advantage of this tree-structured memory hierarchy and take advantage of the fact that referencing things from these register files that's sitting right next to the ALU is essentially free, as in contrast to a big global multi-port register file on a conventional processor, which is not at all free. And referencing from your lane of the SRF is relatively inexpensive, and only rarely do you go out to memory. This is what we provide, the bandwidth in gigabytes per second provided from DRAM, the stream register file, and the local register files on the Imagine chip. These are the demands from those same 4 applications. I apologize for this getting clipped off. That's an artifact of moving from a Windows machine to the Mac. But this is the depth extractor, MPEG, QRD, and RTSL. what you can see is they're actually not stressing the memory a lot, which is good because that's the peak bandwidth of this sync DRAM. And as anybody knows, when they've used sync DRAMs, you don't get the peak bandwidth in anything but unit stride accesses. And they actually don't even stress, except for depth, the SRF bandwidth very much. Most of these are well down from that. But they're making most of their references by far from these local register files where the cost of the reference is small. And that's really where the efficiency of stream processing comes from, is making 95 to 98% of all of your data references from these register files sitting right next to the AOUs. So around 2001, Pat Hanrahan and I were actually sitting at a DARPA meeting where people were talking about programming some scientific application in MPI. We were just both looking at each other and shaking our heads because it sounded like an experience comparable to a root canal without anesthetic. Nobody would really want to do that. And so, we were thinking, why don't people use stream programming for that? Is there any reason, we'd always thought of it as something to use for graphics and image processing and signal processing, sort of UMTS modems and ray tracers and the like. But there's no reason why you can't run your finite element code or your particle and cell code or whatever your favorite scientific code is on a stream processor. What are the differences? Well, instead of having something with 32-bit floating point units, you want something with 64-bit floating point units. So the Merrimac processor is defined with 64-bit floating point multiply add units, 128 gigaflops per chip. And you want a little bit different memory system. Since you actually plan to hook this up into a larger machine, you don't want just this hierarchy of local register, stream register file memory. We actually added a level of cache. I'm not showing that in this block diagram. And the cache is there not for the reason it's on a conventional processor. Caches on conventional processors are there for latency, to basically supply data to the processor with low latency. A cache in a stream processor is there for what I'll call unanticipated sharing. What we found is on some of our codes, in particular our molecular dynamics codes, we would do overlapping gathers. And they would have sufficient overlap, you wouldn't want to have to fetch from memory twice. So if you could have a small cache and then arrange the block size for these gathers, you would wind up getting them once and having the next gather get them the second time from the cache. So they're really a bandwidth amplifier. We don't care about the latency. We've scheduled these operations assuming you had to incur the main memory latency no matter what. So even though you may have supplied it more rapidly from the cache, it actually gained you nothing at all. And then in addition to that cache, we designed a memory system that included going off over a network, both on a board, over a cabinet, and over multiple cabinets. Building petaflops machines was kind of the in thing to propose. So the proposal to build a Merrimac was never built, by the way. We would have built it had they given us the money, but they were kind of stingy about that. The idea is to build a petaflop machine that required 64 backplanes and 32 cabinets to do that. So in contrast to these machines in a lot of DOE labs with many hundreds of cabinets to achieve a small fraction of this performance, a petaflops Merrimac supercomputer would fit quite comfortably in this room. Think of it as 4 rows of 8 cabinets. Now, I can point you to lots of interesting papers on Merrimac, but in the interest of having a little bit of time for Q&A at the end of this, while we did not build Merrimac, we built very detailed simulations of it, down to cycle-accurate simulations of the processor, and we developed the compilers for it. And in collaboration with people here at Stanford in the medical school and mechanical engineering, aero and astro, and other departments, a large number of applications were written for it. So we're able to have a number of these applications. This is sort of a number of applications on Merrimac. Their performance on a simulated Merrimac running at 1 gigahertz. And for a number of these applications, we actually had source code that would compile for a P4. So this is that code running on a P4 at 3 gigahertz. So we're spotting them a factor of 3 in frequency. And even so, and actually I think they even have a slight memory bandwidth advantage. Even so, the speed up we get over the Pentium 4 averages, except for this one code, which I'll talk about in a minute here, more than 15 to 1. So it's sort of more than a 15 to 1 advantage in performance. And that's because we tend to sustain roughly 50% peak performance across this range of applications, where you tend to sustain less than 5% of peak performance on the P4. And it's entirely due to the data supply, due to the cache architecture not being able to adequately supply the floating point units for this class of codes. 2 of the codes here, stream SPAs and stream CDP, you'll notice actually have kind of low numbers for Merrimac. You know, and the peak is 128. If you do dense matrix multiply, this, by the way, is what everybody reports their LINPACK numbers on. We would have really good LINPACK numbers if we built this. I mean, I guarantee you we'd be at the top of the top 500. But we're actually very happy with these numbers as well. There's a chart I don't have here, but what it shows is what percentage of the arithmetic performance you're using on the machine and what percentage of the memory bandwidth you're using on the machine. And both stream SPAs, which is a sparse matrix vector multiply, it's basically what you do in the inner group of a conjugate gradient algorithm, and stream CDP, which is doing a bunch of very memory-intensive operations, hit over 90% of memory utilization. They're basically using all of the available memory bandwidth. And so that's as good as you can do. You basically are keeping the memory system busy all the time. The P4 isn't able to do that even on the same application. It's not quite as far down as it is on the arithmetic limited applications, but it's not able to do that because it winds up locking up its memory system on cache misses and then idling it while you wait for latency, whereas we're able to keep the entire memory pipeline full. The other interesting thing is efficiency. So we had, for the proposal to build Merrimac, which involved a very detailed specification, hundreds of pages in length, which included simulations of big pieces of it and sketches of large parts of the design, we had very accurate power numbers because we basically were assembling units like 64-bit floating point units that already existed. People had the power numbers for them. The memory arrays, people had the power numbers for that. And so we were able to, for these applications, estimate what the power of Merrimac would be to run these applications. And the power numbers are even more impressive. It's 35 to 1 or more for the arithmetic limited applications and more than 10 to 1 for the memory limited applications. And again, that's because you're not burning up a lot of power needlessly moving data and instructions around to reorder things. Your power is going to do useful work. And that's this is actually, I think, also spotting maybe a generation of technology to the P4. So to sort of sum up, the results of our experience, on the Imagine project, what we were able to show is we were able to do about 20 times the performance per unit cost and performance per unit power as the best available digital signal processors of the time. Even though I think we were comparing at that point in time 90 nanometer DSPs to a 0.13 nanometer DSPs to a 0.18 Imagine. And on Merrimac, 10 to 20 times the performance to cost, over 30 times the performance per unit power as clusters and supercomputers. So our experience shows that on real applications, this really works, and the gains are large, factors of 10 or more. Let me wrap up, then I'll have a little bit of time for Q&A. So to go back to sort of our overall outline here, we're sort of into this multi-core era because we can no longer take the transistors that Moore's law gives us every year, and it will continue to give us for at least the next 10 or 15 years, looking at the various roadmaps people have, into performance by building more powerful and ever more complicated single-thread machines. But the good news is that it's easy to build more powerful and very simple parallel machines in this way. But in doing that, what we quickly find is that the arithmetic isn't the costly thing. It's inexpensive in terms of die area. It's inexpensive in terms of power. The costly thing is communication. And so while performance comes from parallelism, and that's inexpensive, efficiency comes from locality, because it's a communication that is expensive. The way to get both parallelism and locality is to build a machine that exposes the expensive thing being communication. You want to expose that communication. That requires building a hierarchical machine. It's not sufficient to have a linear memory hierarchy. At each level of that memory hierarchy, I have to have visibility to which of many sort of co-equal pieces of storage on the die my data is in, so I can make sure that it's co-located with the other data it needs to be operated with and with the arithmetic unit that's going to do the operation. If I build a machine that has sort of an explicit memory hierarchy like this, what we call a stream processor, I now can basically schedule this in a way that makes very efficient use of the scarce resource. I can produce data into a local level of memory hierarchy and consume it out of there without ever materializing it in the memory system, without ever burning expensive global bandwidth. And I can schedule transfers from off-chip to on-chip using sort of just-in-time inventory management techniques to make the most efficient use of this scarce on-chip memory by holding data only during the minimum period of time it's needed. And most importantly, I can factor the surprise out of the inner loops of the program. All the surprise in terms of unpredictable memory latencies is dealt with by doing these bulk memory transfers. And when I fire a kernel off, all of the data it needs, all of the instructions it needs are there, and I can get extremely high utilization by statically scheduling that kernel. We've tried this out both for sort of signal and image processing on Imagine and for scientific computing on Merrimac, and have shown extremely good performance advantages and performance per unit cost and power advantages over other ways of doing it. And in that period, developed a number of very efficient programming systems. And so, what I will posit is, as we move forward and everybody starts building chips with hundreds of cores on them, what is going to matter is finding enough parallelism to keep hundreds of cores busy, but even more importantly, managing the transfer of data up and down this memory hierarchy so that hundreds of cores can share one very skinny pipe off the chip. And the right way to do that is to expose this hierarchy as a tree structure of memories, and then use bulk operations to choreograph the data up and down the tree. So with that, I'd be happy to take any questions you have. Yeah.
So I want to follow up on my previous question because, first of all, the examples you cited continue to be, as you say, signal imaging and scientific. What about the kinds of computation associated with symbolic, object-oriented AI, these kinds of things which are highly irregular, the dynamic structure of computation is not statically predictable. It's okay to imagine, theorem-proving kind of things, as another example. It's okay to imagine that they're expressed in a purely functional thing. So the issue is not necessarily that you're trying to preserve sequential consistency of an imperative programming paradigm, but how do you map this kind of irregular pointer chasing behavior where the pointers you need to chase are based on computation?
Yeah. So that actually happens here. I didn't capture it well. Let me go back to a picture of the memory hierarchy. I also thought I was going to answer your explicit question about what sizes these things were, and it wasn't in any of the pictures, even though I had Imagine and Merrimac stuff. Let me just go over to this side and scan back to the right level. Actually, this slide will do, among others. So suppose I'm doing, well, first of all, I'll say a lot of AI today is machine learning. And machine learning is all about Bayesian networks. And that's essentially doing linear algebra computation. So those applications map onto this really well. But suppose you want to do a Boyer-Moore theorem prover or something like that. And what you're basically going to be doing is a big search. And the good news is that the search frontier is very large. And so I wind up with, think of it, at every point in time, I've got a set of pointers, which are to the next set of nodes I'm going to evaluate. Okay? That's what you gather, that set of pointers. Okay? You then evaluate that set of pointers, which may actually require you then computing a new set of pointers for the next gather. And as long as each of those sets is big enough, right, you have no problem with this model because you've taken the theorem prover and you converted it to a bulk operation model where you have a set of pointers, sort of the frontier of your search. You can gather that set of pointers. You then do operations, right, typically evaluating the node, deciding which children to visit. For each one of those, you compute the set of pointers for the children that you want to visit. You then use that for the next bulk stage, right? That would be the next gather that you do on that. So something like a theorem prover, sort of a logic inference system works just fine as long as that set of pointers is large enough to cover the memory latency. You have to be doing a large enough bulk transfer that it will cover the latency that it takes to do the operation.
So have you tried expressing this kind of computation within your system?
We have not attacked any of those applications. Because of the people we've been working with on these projects, we've tended to focus on signal and image processing for Imagine and on scientific applications for Merrimac. But in some of these scientific applications, there's a lot of pointer chasing when you wind up with building sort of sets and looking for collisions, and there's a lot of sort of cycle-to-cycle irregularity in the data. Yeah, let's move over this way next.
I work for AMD, and so we've invested a lot in superscalar processors and out-of-order execution. And it seems really interesting from what you're saying about factoring out all the surprises by this approach. Does that mean that the type of processor that you need is a lot simpler than a general purpose microprocessor? Like an in-order processor is totally okay for this sort of application?
Yes. So what we've done in both Imagine and Merrimac is the thing that executes the kernels is completely in order. It actually fetches, it's a VLIW. It fetches a very wide instruction word that is 300 some bits wide for Imagine, and I think well over 400 for Merrimac. And it basically fetches them in order, and it actually has somewhat delayed branch because of the latency of that pipe being exposed. In fact, the pipeline is completely exposed, so that if you do an operation, you do the operation. Sometime later, the result falls out the end of the pipe, and you have to schedule an operation there to catch it. And that all works just fine because you factored the surprises out. We do have a very small out-of-order issue unit that sequences the bulk operations. And what it's really doing is it's basically saying that this kernel is dependent upon these two memory transfers being finished and this other interaction with the host happening. And basically it's monitoring those concurrent activities, and when they're done, it fires the kernel off. So we actually have a very modest amount of out-of-orderness at the outer level where the surprises can occur, because we don't know which of those is going to finish first. But at the inner level, because everything is predictable, in order works just fine. And it makes for a really simple processor. Yeah, Dennis.
The obvious application is using this machine to compile code for itself. Have you tried?
No, we haven't done that. It's a good question whether there's enough parallelism in the compiler to keep it busy. I don't know the answer to that.
Well, your search algorithm certainly is parallel.
Yeah, that's true. Yeah.
And that's at the lead.
Good one over here.
How does this interact with protection? That is, how the assumption so far has been the whole machine is devoted to one problem. But if you have a lot of different stuff running, which is mutually mistrustful, how does all this intercommunication interact with protection without taking a trip to the operating system every time you need to talk to another processor?
Okay, so let me give you two different answers to that, one for Imagine and one for Merrimac. So Imagine had no protection. Everything runs, it's basically a DSP. Everything runs on the raw hardware. You can touch every memory location. You need to trust your modules of code. Merrimac was actually designed for a typical scientific computing environment where a large machine is actually shared simultaneously by many people running different jobs who don't trust one another. And so Merrimac had a segmented memory model. Paging, nobody really should do paging. And segmentation is just much cleaner. So Merrimac had a very clean segmented memory model where you would allocate chunks of physical memory in either within a node or across regions of nodes to different users. And then a given computation would have a set of segment registers enabled to be able to look at some subset of the segments that are there. So you can share memory with other processes that you trust by mapping segments the same. You can sometimes share them read-only, so you at least share code images with them. And if you wanted things to be completely isolated, you just don't allow them to touch any of each other's segments. So I think the concepts of stream programming are completely orthogonal from the concepts of protection, which are good because it means you can take everything we know about protection and bring it across, and it works just fine.
But does that mean all the stuff like TLDs and so forth? There's a whole infrastructure in most processors to pass around all the information of who controls what piece of memory. And
yeah, so TLDs are really an artifact of paging, and paging just really doesn't work, at least not in terms of if you're worried about efficiency of machines. And so as soon as you decide that you have to be able to hold your computation in physical memory at a given point of view, you're not going to count on demand paging in virtual memory. The infrastructure is actually very simple. A small set of segment registers, I think in Merrimac it was architected to be 16, is what you need to basically protect memory, and that's the infrastructure. And remember that it's a shared memory machine, so if you have two processors, say you have a two-node machine, if they're part of the same task, they will have identical segments mapped, right? Because they trust one another and they're sharing memory across those segments. And you can have on the same two processors somebody else running a job that doesn't trust that and has a different set of segments mapped. It's using a different block of memory. Yeah, I think there's one over here.
Yeah. Let's go with the stream analogy, right? You have water flowing through a pipe, but if you were to say drop debris in, you get some nasty problems, and they can persist over time, like all the highway traffic around here. So say you have something in Merrimac, like a DRAM failure, right? What's sort of the implication in terms of performance? Because it seems like you know, you have to have facilities to handle those sorts of errors, and that the cost may be high.
Yes. So there's a very comprehensive paper on the reliability analysis and fault tolerance strategy for Merrimac in Supercomputing 05. Because, you know, the plan was to build a petaflops machine. We're going to build a petaflops machine, so failure rates are non-trivial. And so for scientific computation, we don't need real-time performance, but we need throughput. And so the entire fault tolerance strategy for Merrimac is a checkpoint retry. Now, it does have ability to do fault masking of most common fault sources. So, for example, all memory arrays and all communications are checked in such a way that you can do fault masking on them. And then everything is checking, so that you have to be able to check every piece of computation. So one thing that's in the paper is an analysis of the soft error rate of logic as well as memory. And one thing that happens as you decrease line widths is that logic becomes a more significant failure mechanism, where in the past it's usually been memory arrays that have accounted for that. But Merrimac has complete self-checking on all logic, all memory, and you can actually run it in a number of different modes. And there's a great paper on how we basically do that. But the bottom line is that you can calculate the optimum checkpoint restart interval based on the cost of doing that. It winds up being about an hour. So roughly every hour you dump the state of the machine to memory. Since it's completely self-checking, if a failure happens, you detect it. When the failure is detected, you basically you run through a routine where it basically shuts it down, restarts it, and then recovers the checkpoint. And if one node is making more than its share of failures, you basically map that node out and continue on a degraded machine. But I refer you to the Supercomputing 05 paper if you're interested in that. There's a question back there.
So what, according to you, are the major disadvantages of this string computing architecture? And a related question is, are there scenarios where you'd be worse off with this kind of architecture as opposed to general purpose?
So what are the disadvantages of stream processing? I should just tell you there are none. It's wonderful, because it is for most things. But truth in advertising forces me to mention two things. One of them is that if your code does not have sufficient data parallelism, you're not going to get the performance, because the whole notion is really one of hiding latency by doing a bulk operation. So you need a bulk of things to do at once to do that. And the performance is coming from operating data parallel over a large number of units. So if you don't have enough data parallelism in your application, you're not going to get it. But as I think the example of a theorem prover, there's plenty of data parallelism in a theorem prover. It's irregular, and it doesn't have to be regular to use it. It can be irregular, but it has to be there. The other disadvantage, and this is probably why the Merrimac project wasn't funded, is that you can't take your Dusty deck and run it on it. And actually, that may be an advantage rather than a disadvantage, because a lot of the Dusty decks are things that you wouldn't want to play with. But for a lot of people, it's a big disadvantage to approach a new machine and say, oh, before this will do anything useful, I have to rewrite all of my code. That can stop a lot of conversations very quickly. Yeah.
Yeah, it's an interesting architecture, but now you've got all these little pieces, and there's some sort of global clock. You keep the clock in synchrony. Is it a synchronous machine, or are the pieces asynchronous with some sort of queuing between the pieces, or what? And as the machines get larger, the time problems become more and more difficult to manage, even though you, in theory, have a good handle on how long it takes to get a signal from one point to another.
Yeah, so high-speed signaling is something that I've spent a little while thinking about. And it's actually the reason I got into it is we were building supercomputers, and that was the thing that was limiting their performance at the time I started digging into that, because I wasn't happy what people who were working in that area were delivering to me. The plan for Merrimac, of course it was never built, was that every Merrimac node runs on its own clock. And the synchrony is through the network. Now the network actually has been built because we exported the high-radix network ideas that were developed originally for Merrimac, the Kloss network, and that is a network that's used in the Cray Black Widow. And so we've had a series of papers at ISCA 05 and ISCA 06 on the design of that network. And so once you go to high-speed signaling, there's a synchronization that goes on anyway when you basically go from your on-chip clock rate of 1 gigahertz to the SerDes clock rate of 6 1/4. And so you're going through that synchronization, going to the high-speed links anyway. And so there's absolutely no advantage to run the nodes in the machine in clock synchrony, and a lot of disadvantages to doing so. I think we had a question in the back there.
What level of what amount of stalling was found acceptable within the system due to data independencies and bus bandwidth limitations?
So what level of stalling was found to be acceptable? So, so for Imagine, you don't get stalls due to data dependencies because it's statically scheduled. Now, so the stalls that happen in the system happen because of arbitrated resources. And the big arbitrated resource in the system is actually the stream register file. I didn't go into a lot of detail on the architecture, but there are a number of stream buffers because you'd like to be able to have logically many parallel accesses going into the stream register file at once. And you'd like them to be reading a block of data at a time. But you'd like to, for efficiency reasons, make that a single ported memory. So what we do is we actually have a single ported memory and then a structure of buffers that sits between it and much of the arithmetic cluster. And it's counting on a little unit that's sort of operating in the background to keep the stream buffers full before you ask for data out of them. And the one stall that can happen in the system is if you ask for data from that stream buffer and it doesn't have any. There's also an instruction stall that can happen in a similar way. But we haven't found that. If you looked at the performance charts I had, those weren't even in the bar. They happen so rarely that that's not the problem. The overheads that we saw that were important are really time spent in the loop preamble, postamble. And that's because our Imagine, which had 8 kbytes of data per cluster, was not, excuse me, it had 16 kbytes of data per cluster, was not sufficient to really keep, to keep a loop busy. You spent too much time going into it and out of it, not enough time in the loop.
So that should probably be our last question.
Okay.
About 5 minutes after. Just one thing I want to have you comment on is, are you looking for students for research, and are any of your companies hiring?
So I'm always looking for absolutely brilliant students. Right now, my research group is completely full. But if somebody has brilliant ideas, I'm always willing to talk to people. And I believe that Stream Processors does have a number of open recs, and so you should go to the Stream Processors webpage and look at jobs at Stream Processors, and you can be part of the exciting revolution in stream processing.
For information on other online Stanford seminars and courses, please visit study.stanford.edu.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.